Welcome to Robots as Partners, the new frontier, a special episode curated by AI Frontiers. Today we explore 26 breakthrough research papers in robotics, all published on June 25, 2025. This episode highlights how artificial intelligence and robotics are reshaping our world. From real-time perception to human-robot collaboration, we will unpack key advances, innovative methods, and future outlooks, making the latest robotics research accessible to a broad audience. In this episode, prepare for a comprehensive deep dive across the modern robotics research landscape. We will unpack the core advances from 26 newly released robotics papers, revealing the major themes shaping the future of intelligent robots. Key studies will be spotlighted, emphasizing their real-world impacts. Listeners will gain an understanding of how these findings converge to create smarter and safer robotic systems. Finally, we will look ahead to what the future holds and discuss ways for you to engage with this evolving conversation. Robotics serves as the ultimate testbed for artificial intelligence. This field seamlessly blends AI, engineering, and human interaction, focusing on the integration of sensing, decision-making, and physical action. Robotics applications now extend far beyond traditional factory settings, reaching into areas such as infrastructure, inspection, healthcare, agriculture, and more. The discipline faces complex challenges, including uncertainty, real-time responsiveness, and ensuring safe collaboration between humans and machines. The impact of robotics is increasingly evident as these systems transition from industrial environments into the fabric of daily life. The first major theme explored is real-time perception and sensing, a foundational element for autonomous robots. For instance, Girard and colleagues present a model-based system that enables drones to estimate the positions and sag of overhead power lines using sparse and noisy LiDAR data. Girard and collaborators address the calibration of cameras and LiDAR for fast, accurate sensor fusion, while she and team introduce HRI Bench, a benchmark for evaluating how vision-language models interpret human actions in real time. Fast and precise perception, often achieved through sensor fusion, is essential for the reliable operation of autonomous robots in dynamic environments. The second theme centers on adaptive and cooperative planning, enabling robots to learn, coordinate, and respond effectively. Agarwal and colleagues investigate how drones can adapt their routes in real time to rendezvous with ground vehicles for tasks like refueling. Liu and team develop navigation strategies that minimize energy consumption by adapting to changing environments. Pedram and collaborators focus on efficient map sharing among teams of robots, utilizing rate-distortion optimization to balance data compression with information quality. These approaches empower multi-robot teams to coordinate under resource constraints, leveraging rate-distortion theory to ensure effective collaboration while managing limited bandwidth. Human-robot interaction and personalization comprise the third theme, focusing on robots' ability to understand and adapt to their human partners. Janssens and colleagues explore the challenges robots face in detecting miscommunications during dialogue. Fantmail and team review progress in enabling robots to collaborate more intuitively with humans. Bousselade and collaborators demonstrate how federated learning can allow robots to detect human stress through physiological signals, all while preserving user privacy. This adaptability is crucial for building trust in sensitive contexts such as healthcare, where robots must respond appropriately to user needs and emotions. Learning and generalization form the fourth theme, highlighting how robots can acquire new skills swiftly and flexibly. Park and colleagues introduce demo diffusion, a technique that enables robots to learn complex tasks from a single human demonstration. UN and team present behavior foundation models that enable humanoid robots to quickly adapt to novel whole-body control challenges. Wang and collaborators propose a meta-learning approach that allows robots to compensate for positioning errors without relying on vision, inspired by human grasping versatility. Foundation models and meta-learning frameworks collectively facilitate rapid skill transfer and flexible adaptation from limited experiences. The fifth theme addresses robustness, validation, and benchmarking, which are essential for ensuring reliable operation of robots in the physical world. Liu and colleagues introduce statistical frameworks that reduce the real-world cost of validating robotic systems by combining simulation and real data. Xi's HRI benchmark reveals the inherent trade-offs between perception, performance, and speed. Matamala and team highlight the practical challenges encountered during field deployment of autonomous legged robots for forest inventory. The integration of simulation and empirical data accelerates safe deployment, while benchmarking remains fundamental to building trustworthy robotics. Critical insights emerge across these research contributions. Girard and colleagues revolutionize infrastructure monitoring with model-based drone inspection. Park and team make significant advances in generalization through one-shot imitation learning using demo diffusion. And Busselin and collaborators enable privacy-preserving stress detection, allowing robots to personalize assistance without compromising user data. Pedram and colleagues facilitate scalable robot teamwork through efficient map compression. Yuan and team demonstrate how foundation models can dramatically accelerate adaptation for humanoid robots. Collectively, these findings push the boundaries of what is possible in robotics. Various methodologies underlie these advances in robotics research. Model-based estimation and optimization guide real-time robotic actions by leveraging mathematical representations of robots and their environments. Learning from demonstration and leveraging pre-trained policies enable rapid adaptation to new tasks. Multi-objective optimization allows robots to balance competing performance and resource requirements. Simulation combined with statistical validation reduces the risks and costs associated with real-world testing. Federated learning is increasingly adopted to protect user privacy, while still enabling personalized robot learning and adaptation. A closer examination of Girard et al. 2025 illustrates real-time model-based estimation for drone power line inspection. Their approach addresses the challenge of sparse and noisy LiDAR by fitting a geometric model to the entire array of power lines, rather than tracking each wire individually. This method is robust to missing data and outliers, processing each frame in under 50 milliseconds. Tested on real-world datasets, it demonstrated doubled tolerance to outliers, enabling safer and more frequent monitoring of power lines. The paper was selected for its practical impact and robust deployment in operational environments. Park et al. 2025 introduced demo diffusion, a breakthrough in one-shot imitation learning for robots. Their method enables robots to replicate complex human tasks after observing a single demonstration. The process involves retargeting human motion to the robot's end effector and refining the movement using pre-trained diffusion models. This approach outperforms baseline methods and naive retargeting in real-world experiments, making robot learning more accessible and adaptable. Demo diffusion stands out for its innovation in generalization and effective application of foundation models to real robotic tasks. Busselin et al. 2025 present a privacy-preserving system for stress detection using federated learning. Robots assess human stress in real time by analyzing physiological signals such as heart rate and skin conductance, while ensuring that user data remains on device. This federated approach matches the accuracy of centralized models and adapts to individual users, which is vital for applications in sensitive environments like healthcare and manufacturing. The work advances trustworthy, human-centered robotics by combining technical rigor with a strong emphasis on privacy and personalization. Looking ahead, several future directions are charted for robotics research. Improving robot perception in dynamic, complex, or deformable environments remains a priority, especially where sensor data may be sparse or communications limited. Achieving generalization to truly novel tasks with minimal retraining is an ongoing challenge. Integration of physics-based models with artificial intelligence is expected to yield more robust and interpretable robotic systems. Progress in privacy-preserving personalization is essential for real-world adoption. Interdisciplinary collaboration will be increasingly important to ensure that robots are safe, trusted, and beneficial partners. The synthesis and review presented in this episode combine advanced AI tools with human expertise. The content was generated using GPT 4.1 for text analysis, with TTS voiceover provided by DeepGram and visual descriptions created via Stable Diffusion. A human expert reviewed the material to ensure clarity and accuracy, though some oversights may remain. Listeners are encouraged to consult the original papers for complete details. Full references to all discussed papers are provided for those interested in further exploration. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from the arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.